master in node B to the EPC, but user plane can goes from the G node B from 5G directly to EPC as well. So in this case, your control plane will goes from the LT master to the EPC, and your user plane can go directly to EPC or can go from the LT part. We have option 3 for this deployment for non-standalone, which I will go and discuss about in the next page also. But as overall, if I wanted to say about the non-standalone, we can say the NR has been standardized to allow tight interworking with LTE to support the interconnection of LTE and NR base station. So this base station can then use in combination to serve the population of the user equipments UIs. Actually, non-standalone architecture allows a smooth and relatively simple evolution toward the complete end-to-end 5G system. Also allows to reuse of current and existing LTE base station and existing 4G core network, as I said. In general, a software upgrade is sufficient to allow interworking with a set of NR base station. So as a general, we can say NR is working in a non-standalone way as an extra carrier to LT. Initial access, control plane termination, QoS is managed by the LTE node B, and NR user plane either via LTE node B or directly to EPC. And also mobility control is split between the LTE and NR node, which for more detail about these concepts and functionality, we will discuss about these things in the next presentation and next clips. But we have an SARAN option 3, which you can see in this here, which control plane of the NR and user plane both goes from the LTE master in node B to the core part EPC. We have 3A option, which control plane will goes from the LT part, but user plane of the NR will directly connected to the EPC. And 3X option, which is the control plane will goes from the LT, but LT user plane also will goes from the NR, and NR user plane will directly connected to the EPC. So centralized and distributed deployment option. Actually, NR base station have a flexible architecture which support a range of deployment options. First option, classical base station architecture can be adapted to keep the hardware within a single cabinet. But the second option is alternatively the base station can be split into the centralized unit and the distributed unit. The centralized unit accommodate the higher protocol stack layer and control the operation of one or more G node B DOS. Let me put these charts, you can see in more detail. The centralized unit accommodate the higher protocol stack layer and control the operation of one or more G node B DOS, while the distributed unit accommodate the lower protocol stack layer and host RLC, MAC, and physical layers of the G node B. Also, its operation is partly controlled by the G node B centralized unit. A single centralized unit can host a large number of distributed units, typically greater than 100, while each distributed unit can host multiple cells, typically greater than 6. As a general, we can say G node B centralized unit hosts RRC, STAP, and PDCP protocol of the G node B. In addition, the centralized unit can be split into control plane and the user plane functions. This allows independent scaling of the control plane and user plane processing capabilities. It also allows the two functions to be deployed at the different geographical locations. So user plane functions may be located in close to the distributed unit to help reduce user plane latency, while control plane functions may be centralized to pool resources. As you can see here in this picture, we have F1 interface is higher layer front hall interface being between PDCP handled in the G-Node B centralized unit and the RLC handled in the G-Node B distributed unit. It has been standardized by 3GPP to allow for multi-vendor control unit and centralized unit and distributed unit deployments. So this was the difference between the classical base station and centralized unit and the distributed unit. Here I'm going to explain you the difference between the LTE versus 5G. The first difference is the 5G NR occupy higher spectrum for same spectrum mask. For example, for 20 MHz bandwidth, LTE usage is 90%, while 5G NR usage is greater than 95%. So here you can see in the same bandwidth, if you use the 20 MHz in 4G and 5G at the same time, you will see the bandwidth in the LTE will be 18 MHz and 2 MHz will be used for the guard band. But in the 5G it will use 19.2, means 0.8 MHz will be used for the guard band. Because of in the 5G we are using the filtered OFDMA. Also we are using the filter OFDMA, so we can use more bandwidth in case of 5G technology. So we can say a spectral efficiency, it will increase in the 5G NR. So in this case, we can have some other reasons as well, which the difference comes from the tighter RF requirements, tighter emission, adjacent channel leakage ratio ACLR, and selectivity requirements both for TX and RX in the 5G NR technology. Even though if that's why you will have the more throughput in downlink direction in the same configuration between the 4G and 5G. Think about you have same this 20 MHz bandwidth in 4G and 5G, and you have this, for example, FDD 20 MHz 4x4 MIMO to 256 QAM, and subcarrier spacing is 15 kHz in both LTE and 5G. But in the 4G maximum throughput it will be 413 megabit per second, but in 5G it will be more than this, and it will be around 450, I think 53 megahertz throughput in 5G you can achieve. Also you can see here with 18 megahertz you will have 100 PRB, but in case of 5G you will have in same bandwidth you will have 106 PRB in this case. 5G NR brings connectionless protocol. As you already know, in LTE, in the second difference between 4G and 5G, I said this connectionless protocol. In the 4G we have two states, RRC idle and RRC connected, which you know there is a lot of RRC signaling and it will happen overhead for the signaling. But in the 5G, a new state which is related to RRC connected inactive, which will minimize the signaling and overhead in the 5G technology. The third difference between the LTE and 5G will be the 5G NR has higher expected downlink spectral efficiency. You can see in this table, which simulation is from some assumption, you can see in the same configuration in 5G network you will have the more spectral efficiency compared with the 4G advanced. So the reason will be the PDCCH usage. As you know already, in LTE PDCCH exists in every subframe, but in NR introduced a slot aggregation concept, and it is not mandatory to have PDCCH in all TTIs. Second reason will be usage of guard band, which I said in the previous slide about the filter OFDMA, which use less bandwidth for the guard band in the 5G technology. And the third reason will be about the TBS concept. As you already know, the 4G has one TBS, whereas in NR use concept of CBG. They're saying the code block group, which divide the TBS into small groups. Like we can say, as 5G use huge TBS and blur. As blur is around 10%, which means with this TBS around 10% of data will be transmitted, whereas with this technique in 5G UE will send NAC only for discarded groups. So this is the main difference of TBS size and allocation between the 4G and 5G. The fourth difference will be the link area. As I said before, in LT, CRS used to estimate, in LTE, CRS used to estimate channel, and it is transmit always in 4G, whereas in 5G tries to eliminate the use of CRS. So you can see in this picture also, CRS always is transmitting in the LTE frames, but in the 5G NR, it will not mandatory to transmit always. And you can say in 5G user specific DMRS used, which means each use will have its own RS within its allocation. If there is no allocation, there is no RS. Also in here in the channel, control channel, we can see in 5G SSP blocks, which is related to PSS, SSS and PBCH channel. Block is always transmitted, and this always has its own RS, which can be used for cell selection. Later you will use its own RS and will have no issue. So finally we can say with the link carrier technique, intercell interference will minimize from reference signal, and this is one of the big achievements in the 5G technology. But actually we have in current LTE as well this link carrier. We have this feature, for example, in this LTE current LTE network, but there is some issue and conflict with other feature which is not that much used in the current LTE network, but it is enhanced and improved in the 5G technology, and this is one of the main difference between the LTE and 5G technology. 5G NR compared with the LTE improved the energy efficiency also, and the final and the last difference will be the 5G NR minimize IoT device power consumption. The major potential in improving IoT device battery lifetime and LTE connection duration. If I show you in these pictures, you can see the major potential in improving the IoT device battery life. This is the reason of the difference between the 4G and 5G. As you know, the LTE connection duration always is greater than 10 seconds, even for the small data transmission. But what is the 5G solution? As we said before, the RRC in active state and non-orthogonal uplink. So this is the factor of 100 times improvement of potential in battery life for these IoT devices. So this was the LTE versus 5G NR difference. Thank you so much. Here I finished the 5G NR Overview Part 1. In the Part 2 video, we will discuss about multiple numerology, millimeter wave, beam management, LDPC polar, and SDAP layer. Thank you so much. This is my LinkedIn and my Gmail address. Please contact and send if you have any comment or any feedback regarding this presentation. I will upload the second part of this overview as soon as finished. Thank you so much.